To really get a handle on the universe, quantum mechanics tells us to start small. I mean, ridiculously small. We're going to simplify everything, and I mean everything, down to just a single particle moving on a straight line. Now that sounds almost too simple, right? But by doing this, by isolating it, we get to uncover the truly bizarre fundamental rules that govern reality itself.
So that's the big question for us today. What are the absolute rock-bottom rules for a single particle? If you strip away everything else, all the noise, all the complexity, what laws must it obey? Let's just forget about atoms and molecules for a minute. We are starting from absolute scratch.
So here's our game plan. First, we're going to shrink our universe down to a single dimension, just a line. Then we'll let a particle go and see what it does all on its own. After that, we'll trap it in a box, and then, just for fun, we'll throw a wall in its path. With each step, we're going to reveal another incredible piece of this quantum puzzle.
Now, physicists love thinking about problems in one dimension. And it's not because they think the universe is some kind of flat line. It's because it's the perfect laboratory for ideas. When you strip away all the messy complications of 3 dimensions, the core rules of quantum mechanics just pop out with crystal clarity.
In this quantum world, the official rulebook, the law of the land, is the Schrödinger equation. Now, don't worry about the math. You don't need to solve it. What's important is knowing its job. It's the fundamental law that predicts the future of a particle. It tells us how its wave function, which is just the complete description of its quantum state, changes and evolves over time.
All right, let's use that rulebook on our first test case. Imagine a single particle, totally free, just cruising through empty space. Sounds like the simplest thing you could possibly imagine, but this is exactly where we see the first huge break from the world that you and I are used to. Okay, think about a normal marble rolling across a table. At any given moment, you know exactly where it is and where it's headed, right? It has a definite position, a definite momentum. A quantum particle, though, it's described by something totally different, a wave packet. It's not a tiny point, it's more like a localized bundle of probabilities. So what is a wave packet? Well, you can picture it as a little wave that's all bunched up in one area. The height of that wave at any particular spot tells you the probability of finding the particle right there if you were to look for it. You see, in the quantum world, location isn't a fact, it's a game of odds. And here's where it gets really interesting. Look at what happens over time. At the very beginning, the packet is nice and tight. We have a pretty good idea of where the particle is, but as it moves, that wave packet just naturally spreads out. This doesn't mean the particle is physically getting bigger. No, it means our uncertainty about its location is growing. The probability of where it could be just gets smeared out over a wider and wider area. For a free particle, this growing uncertainty is totally inevitable.
So, a free particle gets more and more uncertain over time. But what happens if we don't let it? What happens if we try to force it to be certain? What if we trap it inside a box, confining it to one specific region of space?
The logic here is just beautiful. First, we know the particle acts like a wave. Second, if it's trapped in a box, its wave function has to go to 0 at the walls. I mean, it can't exist outside the box, right? This condition forces the wave to fit perfectly inside, kind of like a guitar string that's pinned down at both ends. And what happens with a guitar string? It can only vibrate at specific frequencies, specific wavelengths. And here's the real kicker. In quantum mechanics, a particle's wavelength is directly tied to its energy. So if only certain wavelengths are allowed, then only certain energy levels are possible.
And this leads us to one of the most profound, most famous ideas in all of physics, energy quantization. A particle in a box isn't free to have any old energy it wants. Nope, its energy can only exist in these specific, discrete packets called quanta. It can have energy level 1 or energy level 2, but it is physically impossible for it to exist anywhere in between. This is what that energy ladder looks like. You've got the lowest possible energy, called the ground state. The next allowed step up isn't just a little bit more, it's 4 times that ground state energy. The one after that, 9 times the energy. The rungs on this ladder get farther and farther apart the higher you climb. And this entire structure, this whole set of rules, was created just by putting the particle in a box. This isn't just some neat little math trick. It's a revolutionary discovery. As the physicist R. Schenker puts it, the particle in a box is our first encounter with the quantization of a dynamical variable. It's the moment we realize that a property like energy, which we always assumed was smooth and continuous, is actually grainy. It's pixelated at the quantum level.
Okay, we've seen a particle that's totally free, and we've seen one that's trapped. Now for the strangest rule of them all. What happens when a quantum particle runs up against a wall that it absolutely should not be able to get through?
In our world, this is a no-brainer. If you roll a marble towards a hill it doesn't have enough energy to get over, it will always, 100% of the time, roll back. End of story. But a quantum particle? Well, that plays by different rules. Even if it doesn't have enough energy to climb over the barrier, there's a real measurable chance it'll just appear on the other side.
So how on earth is that possible? Well, it all comes back to that wave function. When the particle's wave hits that barrier, it doesn't just stop cold. It actually penetrates into the wall. Now, inside this forbidden zone, the wave starts to die out really fast. It decays exponentially. But if the barrier is thin enough, the wave might not decay all the way to zero before it reaches the other side.
This absolutely ghostly behavior has a name: quantum tunneling. It's the phenomenal ability of a particle to pass through a barrier that, according to all the laws of classical physics, should be totally impenetrable. It's like a ghost walking right through a solid wall.
And look, this isn't just some theoretical quirk. This is fundamental to how our universe works. The sun shines because protons tunnel through their electrical repulsion to fuse together. The computer or phone you're watching this on works because electrons tunnel through tiny barriers inside its transistors. This impossible quantum leap is literally happening all around us all the time.
So, let's just take a breath and zoom out for a second. From just these three incredibly simple scenarios, we've managed to uncover three radical new rules for reality itself.
Let's just do a quick review. The free particle taught us about the unavoidable nature of uncertainty. The particle in a box showed us that energy comes in discrete chunks, it's quantized. And the particle at a barrier revealed quantum tunneling, the power to do the impossible. In every single one of these cases, our everyday intuition completely and utterly fails us.
But, and this is so important, as strange as these new rules are, they are not random. Quantum mechanics is built on a solid foundation of precise mathematical laws. For instance, there's a theorem that says for a particle trapped in one dimension, each allowed energy level corresponds to one and only one specific quantum state. There's no ambiguity. The weirdness is predictable.
And that's why we care so much about these simple problems. They are the ABCs of reality. Uncertainty, quantization, tunneling, these aren't just parlor tricks that happen on a straight line. They are the fundamental principles we use to build our understanding of everything from atoms and molecules to the incredible technology that powers our world. So if you take anything away from this, let it be these three pillars of the quantum world. First, uncertainty. Particles are really just waves of probability. Second, quantization. Trapping a particle forces its energy into specific, discrete levels. And third, tunneling. Particles can defy barriers that should be impossible to cross.
We've seen just how profoundly strange a single, isolated particle can be when it's all on its own. But that, of course, raises the ultimate question. If one particle is this weird, what in the world happens when they start to interact with each other? Well, that's where the quantum world gets truly, wonderfully wild.